Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will go through everything you need to know for the upcoming test. So the test is on Wednesday, week 3, and we'll cover the topic of similarity. But just before we jump into similarity, we'll briefly go over what congruence means and compare and contrast this with similarity. So I have two triangles here on the screen that are congruent to each other. So what that means is essentially I can take the second triangle and I can fit it perfectly on top of the first one. So the first triangle and the second triangle are just transformations of each other. So I can flip the triangle or rotate it or whatever, and they will still be congruent. I will still be able to put one exactly on top of the other. So congruence essentially means that I can put one on top of the other. So in order to be able to do that, they have to be exactly the same shape and size. So what that means is pairs of corresponding angles will be the same, pairs of corresponding sides will be the same. So similarity is a slightly different concept. So draw up another triangle here. So if I create another triangle like this and I enlarge it, the two shapes are similar. So that's what similar means. They're not the same shape when they're similar. You can see clearly the second one is much bigger than the first. But what they are is they are the same shape, but not the same size. So we saw for congruence, they needed to be the same shape and the same size, but here they're the same shape but not the same size. So in order to be the same shape but not necessarily the same size, we need two conditions. So we need them to have the same set of angles and we need all the sides to be in proportion. So corresponding angles must be equal. So if these two shapes are going to be similar, then this angle and this angle would need to be the same, and so too this angle and this angle would need to be the same, and also this angle and this angle would need to be the same. But not only do shapes, in order to be similar, need to have the same angles, they need to have all sides in proportion. So what that means is you can multiply each side of the smaller shape by the same number to get the side in the larger shape. So for example, let's say we had in this triangle was 4, 4.5, and 5, for argument's sake, okay? It doesn't need to be drawn to scale. So if the larger one was similar, its sides need to be in the same proportion. So that means if this side here was 8, this side 8, which corresponds to this side here, then over here, this side would need to be 9. It would need to be double 4.5, and this side down the bottom would need to be 10. So these two shapes would be similar because they have the same set of angles and their sides are in proportion. Because if you take any side in the larger shape, divide it by its corresponding side in the smaller shape, you get the same number. So each side of the larger shape is double its corresponding side in the smaller shape. So this number that we've multiplied the smaller shape by to get the side in the larger shape, that is called the scale factor. So here, 2 is the scale factor, meaning every side in the larger shape is 2 times its corresponding side in the smaller shape, okay? So all the sides need to be in the same proportion. So if I rubbed this out and now told you that this side was 11, the two shapes would no longer be in proportion. They wouldn't have the same proportion. It will, of course, mean that this angle here would be like slightly different or whatever. So we can't have that. All sides need to be in the same proportion. Okay, so that's what it means if two shapes are similar. So fortunately, for triangles, they present a special case. If I want to determine whether or not two triangles are similar, I don't need to check every pair of sides and every pair of angles. I can use some shortcuts, which we call tests, which I'll go through on the next slide. So please pause and copy this down if you need. So there are 4 tests that we can use, and they're all listed here: SSS, SAS, AAA, or RHS. So these are almost the same tests as for congruence, except instead of AAS for congruence, there's AAA for similarity. So here, S is talking about a pair of sides in proportion, and A is talking about a pair of angles equal, okay? So please note the difference there. S doesn't mean the sides are equal, it means they're in proportion, whereas A means the angles are equal. So the RHS has a few different letters. So R just means that both triangles are right angled, and H is talking specifically about the hypotenuses being in proportion. So remember, the hypotenuse of a right-angled triangle is the longest side of that triangle, and it faces the right angle. So you can only use this last test in a right-angled triangle. So what these tests are saying, so the first one, SSS, is saying that if all 3 pairs of sides are in the same proportion, then the 2 triangles will be similar. I don't need to check whether or not the angles are equal. I know they will be, because this test is enough to prove similarity. So this second test here is a little tricky. It's 2 pairs of sides in proportion, but it has to be the angle between the 2 sides that are in proportion. It can't be any pair of angles, okay? AAA is self-explanatory. 3 pairs of equal angles, that means that the sides will be in proportion. So if you have 2 triangles and they have 3 pairs of equal angles, I don't need to check whether the sides are in proportion because I know they will be. And similarly for RHS. If both triangles are right-angled and then the hypotenuses and another side are in the same proportion, I don't need to check the other side and the angles. I know that they will be similar. So remember, these tests mean that 2 triangles are similar, and if 2 triangles are similar, pairs of corresponding angles are equal and pairs of sides are in the same proportion. So let's go through and look at how we might use these tests. So we have 2 triangles here, and we want to see whether or not they are similar. So what we do, we don't just look at it and say, oh yeah, one looks like an enlargement of the other. We see whether we can use any of the tests. So we haven't been given any information about angles here, so I don't want to use any of the last 3 tests that involve angles. I'm going to try and use the first one. So, are the sides in proportion? Well, we want to line up corresponding sides. So line up the longest side of each triangle. So 55 over 22, and then we line up, say, the shortest side of each triangle. So 10 and 25. So we want to see whether these are equal. We want to see whether 55 over 22 is the same as 25 over 10. And then we want to see if that is the same as 45 over 18. So what we do is we just put all of these in our calculator. So if you put 55 over 22 into your calculator, you will get 2.5. If you put 25 over 10, you get 2.5. And same with 45 over 18. These all give you the same number. So that means that each side in the larger triangle is 2.5 times its corresponding side in the smaller triangle. This means that all the sides are in the same proportion. So these 2 triangles are similar by the SSS test. And 2.5 is the scale factor. So would these 2 triangles here be similar? So let's see if we can use any of the tests. So we have a right angle and we have two other sides. So let's see whether those two sides are in proportion. So again, what we want to do is we want to line up the longest side of each triangle, and then we're also going to line up the other side of each triangle. So if I put in my calculator 30 over 10, you should all know that that's 3, and that is the same as 12 over 4. So these two pairs of sides are in the same proportion. We also have a right angle. Now note 30 and 10 are the hypotenuses of their respective triangles because they're the longest side facing the right angle triangle. So we have a right angle, we have the hypotenuses, and another side in the same proportion. So these two triangles are in fact similar by the RHS test. All right, so we're now going to do a few more that are slightly more complicated, so please pause and copy this down if you need. So let's look at these two triangles here and see whether or not they are similar, okay? So what we have here, we don't quite have information to use one of the tests yet. So what we have to see is if we can get enough information. So note that this angle and this angle, they will be equal because they are vertically opposite. So what we have here, we have a pair of sides here and here. But we don't have another pair of sides. This 10 here, there's nothing to compare them to. I don't know whether 12 and 6 are in the same proportion as 10 and its corresponding side, which would be this one down here, because I don't know its length. So I only have one pair of sides. So note, none of the tests involve just one pair of sides. They either involve 2 or 3 pairs of sides or none. You can't have just one pair of sides being in proportion. Now, you can't say that this angle and this angle are equal. We don't know that. We would need to be told that this line and this line are parallel. So since we weren't told that, we don't have enough information to find any other equal angles here. So what we have is one pair of equal angles, but we only have one pair of side lengths. So we don't have enough information here to conclude that they are similar. We don't know that they're not similar, but there is not enough information here to use any of the tests. So let's look at these two triangles down the bottom. So we have this smaller one here, and then we have this larger one here, okay? So, are they similar? Well, I've been given absolutely no information about the side lengths, so I can't use any of the tests involving side lengths. I can't use SSS, SAS, or RHS, because all of those involve using the side lengths. So don't have that. My only choice when I'm not given information about the sides is to try and use AAA. Now, in this case, I would need to find 3 pairs of equal angles. Well, firstly, note this angle is in both triangles, so it must be equal in both triangles. So now we need to see, can I find any other pairs of equal angles? Because I can't use any of the tests involving sides. I don't have any side lengths. So because this line here and this line here are parallel, that's what the arrow means, these two angles here must be equal. They are corresponding. So once you have 2 pairs of equal angles, the third pair must also be equal because the angles in any triangle add to 180. So if the black angle is equal in both triangles and the green angle is equal in both triangles, then these 2 angles must be equal as well. So these 2 triangles, the smaller one and the larger one, they are similar by the AAA test. So in the test, you won't actually be asked to formally prove that 2 triangles are similar, but you will need to be able to explain why 2 triangles are similar and apply the tests. So when you have explained that 2 triangles are similar, or when you're told that 2 triangles are similar, we can use that information to find unknown sides or angles. So finding angles are really simple. So for example, if I told you that this angle here was 48 degrees and I said find the angle here, well, that's actually really simple. They are corresponding angles and they must be equal. So I will just be 48 degrees. But let's have a look at an example where we're finding unknown side lengths. So we're going to use what we know about similar triangles to find the side lengths Z and X. So whenever you want to find a side length, an unknown side in similar triangles, or any similar figures for that matter, the first thing you need is the scale factor. So remember, that is the side in the larger triangle divided by the side in the smaller triangle. So note, this side that's 16 and this side that is 10, they correspond to each other because they are the sides in each triangle that have the black angle and the yellow angle touching it. So they correspond to each other. So the scale factor is the larger side divided by the smaller side, which is just 1.6. So here is the rule for finding an unknown side in similar triangles. So the rule is, if you want to find a side in the smaller shape, the smaller triangle, you divide by the scale factor. And if you want to find a side in the larger triangle, you times by the scale factor. So note here that X is in the smaller triangle. So what we do is we take its corresponding side, which is 12, and we divide by the scale factor 1.6. And you can just put that on your calculator. You should get X is 7.5. So note here Z, we're looking at a side in the larger triangle. So what you do is you take the side corresponding to Z. Now this time, because Z is in the larger triangle, we're going to times by the scale factor, which is 1.6. And that gives us 14.4, okay? So you'd expect that Z would be larger than 9 just by looking at the diagram. Similarly, you'd expect that X would be less than 12, okay? And our answers did confirm that. So just make sure that you, when finding the scale factor, always do larger shape divided by smaller shape, side length in the larger shape divided by its corresponding side in the smaller shape, and then you can use the rule that you always divide by the scale factor to find a side in the smaller triangle, and you times by the scale factor to find a side in the larger triangle. So one more thing I need to show you how to do is write a similarity statement. So to show you, I'm going to give each of these vertices letter. We're going to write a similarity statement. So a similarity statement is one that says triangle blah 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 is similar to triangle blah blah blah. So I can call the smaller triangle, whatever I want, as long as I use the right letters. So it's got vertices C, B, and E. That's the smaller triangle. So I can call it triangle CBE or BCE or whatever. So I'm going to call it triangle BCE. Okay, so triangle BCE is similar to, so you either use this symbol here or you can use this squiggly line here. Either one doesn't matter. They mean the same thing. So when you're writing the vertices of the second triangle, they need to correspond to those in the first. So what I mean is, because I wrote B first in the first triangle, the first vertex of the second triangle has to be the one that corresponds to B. So how can you tell? Well, note, this angle at B is the same as the angle at A. They're the same angles. So B corresponds to A. So I'm going to write A first in the second triangle. So look at the angle at C. Well, it's equal to the angle there. It's equal to itself. C is in both triangles. So C corresponds to itself, and you can see that the angle here at vertex E is the same as the one at D. So E and D correspond. I write D last. So that is the similarity statement. Triangle BCE is similar to triangle ACD, and we usually just put the test in brackets. Okay? So it's important when you're given two triangles, that you will be able to use the tests to determine if the triangles are similar or if there is not enough information. It's important that you can use similarity to find unknown sides in both the larger triangle and the smaller triangle, like I just showed you, and also that you can write similarity statements. So the next thing I need to be able to show you is how to actually start with a triangle and enlarge it and draw a shape that is similar yourself. So please pause and copy this down if you need. So what we need to be able to do here is take a shape like the triangle and enlarge it or reduce it about a center of enlargement. So what you need to be told to be able to do this is the scale factor you're using. So if the scale factor is more than 1, then what you draw is going to be larger. You're making the shape larger. And if the scale factor is less than 1, then you are making the shape smaller. So I need to tell you the scale factor. So in this case, I'm going to tell you the scale factor is 2. So what I'm going to do is label my vertices however you want. I'm just going to call them A, B, and C. Now you measure the distance from each vertex to the center of enlargement. So let's say that the distances are 3, 4, and 5. So how am I going to enlarge this by a scale factor of 2? So what I want is a triangle that's the same shape, same angles, but each side length is double the original. So what I'm going to do is I'm going to double the length of each of the lines I've just drawn. So what I mean by that, so this distance here is 3, so I'm going to keep going with the line, so it's now doubled. So the distance from the center of enlargement to here is not 3, it's now 6. So that's where C is going to go. So I label it C dash. Now I'm going to do the same with B. So I'm going to draw a line that is double the length of the original line. So it's going to be out around here, and I'll call that B dash. Okay? Now we do the same for A. So I draw a line, same direction, that's double the length of the original. So this line, started as 4, will now be 8. So A moves there, and I put an A dash. So when you figured out where all the vertices go, all you need to do is join them up. So the triangle I've just drawn in red is the same shape as the original triangle, it's just its side lengths will be doubled because I doubled the distance of each vertex from the center of enlargement. So what would the area be? Would the area also double? Well, no, it won't. The area will actually be multiplied by the scale factor squared. So the area will have increased by 4 times. So the side lengths will double, but the area will quadruple. And that would work for any scale factor. If the scale factor was 3, the side lengths would triple, but the area would be multiplied by 9. I could also do one where I make the shape smaller. So if I make the shape smaller, let's now do one in green where the scale factor is 1/2. What I do is I just halve the length of each distance from the center of enlargement. So I'd move B dash to about there, so it's only 2.5. I'd move A to about there, so it's only a distance of 2 away from the center of enlargement. I'm going to call them double dash these times to avoid any confusion. And similarly, C will be about halfway, a distance of 1.5. Okay? So then I draw this triangle in green. So it will have side lengths that are half the length of the original triangle. Its area will be 1/2 squared, which is 1/4 of the original shape, okay? So when you multiply the sides by k, the area is multiplied by k squared. So that's how you make similar figures using the center of enlargement, okay? And I apologize, my drawings aren't the best on the iPad. So the very last thing I need to show you is just how to solve a couple of problems. So let's look at finding x in this triangle. It will be difficult just because of where x is positioned, but we won't do it really any differently than how we found an unknown side on the previous slides. So firstly, note we have 2 triangles here. So the big triangle, I'll just call triangle AEB. B. So that is similar to triangle. So the one that corresponds to A is D, E corresponds to itself, and B corresponds to C. Okay, so why will they be similar? Because of A. We don't have enough information to use any of the tests involving sides because we only have one pair of sides. In fact, 9 actually isn't the side of a triangle. The side of the triangle is 12. So we have to use AAA. So this angle here is common, and as I showed you in an example before, this one and this one are corresponding, so they're equal, and this one corresponding, so they're equal. So the triangles are similar. We've got that out of the way. Now, if I want to find x, as I told you before, we need to find the scale factor. So most people will say, oh, the scale factor is just 9 over 3. How easy is that? But it's not. 9 is this length here. It's not the length in a triangle. The whole length here in the big triangle is actually 12. So the scale factor is not 9 divided by 3, it's 12 divided by 3, which is equal to 4. So how would I find x? Well, we know that this side here, which is 7.5 plus x, must be 4 times this side here, which is just x. We know it has to be 4 times that because the scale factor is 4. So if I go through and solve this equation, I want to subtract x from both sides. Remember, when you're solving an equation and x is on both sides, you subtract the one with the lowest coefficient. So I get 7.5 equals 3x. The x's cancel out. 4x minus x is 3x. Just divide each side by 3, you get 2.5 is equal to x, okay? So that's just more of a problem-solving question that's a little more difficult. Now let's look at a worded problem. So let's attempt this question here. At the same time of day, a tree makes a 16-meter shadow and a person who is 1.8 meters tall makes a 1.2 meter shadow. How tall is the tree? So you might think, oh my God, what does this have to do with similar triangles? Well, we wouldn't be asking any question in the test that doesn't have anything to do with similar triangles. So what we're going to do is we're going to draw a diagram that involves similar triangles. So we have a tree here. So the tree, which we don't know its height, so we'll call that x because that's what we want to find. So it makes a 16-meter shadow. So we'll turn this into a triangle. So at the same time, a person who is 1.8 meters tall makes a 1.2 meter shadow. Now, because tree and person stand perpendicular to the ground, we have right angles. Also, because it's the same time of day, the angle that the sun makes with both the tree and the person will be the same. The angle made by the sun will be the same. So this angle and this angle will be equal. So because I have a triangle in which 2 pairs of angles are equal, they must be similar. The third pair of angles must also be equal. So these 2 triangles are similar. So how can I find the value of x? Well, it's just like we did in the previous example. Firstly, what we need to do is find the scale factor. So the 2 sides that correspond here, we have the scale factor is 16 divided by 1.2. And that gives us 13 1/3. The scale factor does not have to be a whole number. So if you get a decimal, please don't think you've done something wrong. So then, now we're going to find the tree. So the tree, x is in the larger triangle. So what we do is we take the corresponding side and we times by the scale factor. And then if you put that on your calculator, you get 24. So the tree is 24 meters tall. So that's an example of how we can use similar triangles to measure inaccessible objects. All right, I'm sorry for the long video. Best of luck studying. This has been the luckiest maths teacher in the world. Have a great day.